Hi, today I'll be talking about enzymes as part of the MCAT Biochem review. As for classification of enzymes, there are 6 different enzyme types that you should know for the MCAT. First is the oxidoreductase. Oxidoreductases catalyze oxidation reduction reactions, also known as redox reactions, and this involves the transfer of electrons between biological molecules. Because it involves electron transfer, oxidoreductases often require a cofactor to accompany it in catalyzing a reaction. Some common cofactors are NAD plus and NADP plus. And when you see an enzyme with the name dehydrogenase or reductase, you can assume that it's an oxidoreductase. Transferases catalyze the movement of a functional group from one molecule to another. In this example reaction below, aspartate aminotransferase catalyzes the movement of an amino group from aspartate onto alpha ketoglutarate. Kinases are another example of a transferase. Kinases catalyze the transfer of a phosphate group, generally from adenosine triphosphate or ATP, onto another molecule. Hydrolases catalyze the breaking of a compound into 2 molecules using water. Some examples include phosphatases, which cleave a phosphate group from another molecule, as you can see in the example. Alkaline phosphatase cleaves phosphate monoester using water into an alcohol and a phosphate. Lyases catalyze the breaking of a compound into 2 molecules without water. And that's the key difference between a hydrolase and a lyase. Whereas hydrolase uses water to break a compound, lyase does not. Because the reactions that lyase catalyzes are normally reversible reactions, the opposite reaction gives the enzyme a new name. Lyases catalyze the breaking of a compound into 2 products, the forward reaction, whereas synthases catalyze the reverse reaction, a formation of one compound from 2 reactants. Isomerases are enzymes that catalyze the rearrangement of bonds within a molecule. Here, malleate isomerase changes malleate into its constitutional isomer, fumarate. When you see reactions between stereoisomers as well as constitutional isomers, you can assume that isomerases are involved. And I'm just now realizing that I misspoke. Malleate and fumarate are stereoisomers, not constitutional isomers. Ligases catalyze the addition or synthesis reactions between large similar molecules, and they often require ATP in order to do so. Here, a common example of ligase can be seen in DNA synthesis or DNA repair. Here, this ligase catalyzes the addition of one large DNA strand onto another large DNA strand. Some important things to remember about enzymes and activation energy. First, the difference between endergonic and exergonic. Endergonic reactions require energy. This means the delta G is greater than 0, and the reaction is non-spontaneous because it does not happen on its own. It requires an energy input in order to proceed. Exergonic reactions, on the other hand, release energy. This means delta G is less than 0, and the reaction is spontaneous because it occurs on its own. It does not require energy, but rather releases it. Another important thing to remember is that enzymes are not a thermodynamic molecule. They are kinetic. And this means that they don't alter thermodynamic properties, such as the overall free energy change, the delta G, or the equilibrium. Enzymes, however, do affect things like reaction rate. So it increases the rate at which a reaction gets to equilibrium, but does not change the actual equilibrium itself. And the way enzymes increase reaction rate is by lowering activation energy. This makes it so that it's easier for a reaction to reach its transition state. On the right here, you can see a perfect example of that. This is an exergonic reaction. The green curve shows the reaction in the absence of an enzyme, whereas the red curve shows the reaction progress in the presence of an enzyme. As you can see, the activation energy, denoted by these arrows, is greatly decreased in the presence of an enzyme. That makes this transition state right here much easier to reach. Mechanics of enzyme activity. So there are two theories of enzyme substrate binding. The first is the lock and key theory. And this suggests that the active site of the enzyme is already in the correct shape to fit the substrates. There's nothing that the substrates need to do other than fit themselves into the active site. On the other hand, the induced fit model, which is the more scientifically accepted model, suggests that these substrates, when coming in contact with the enzyme, induce a conformational change in the enzyme, then allowing the substrates to fit and allowing the substrate complex to form. Inducing this change in an enzyme is endergonic, whereas going back to the original shape is exergonic. You could think of this as like squeezing an object. When your hand squeezes an object, that requires energy. That inducing a change in that object is endergonic, whereas when you release the object back to its original shape, this is an exergonic process because it does not require additional energy input. That's just one funny way to think of it. Cofactors and coenzymes. Cofactors and coenzymes are basically things that accompany enzymes. They bind to the active site and they accompany the enzyme in catalyzing a reaction, usually by carrying charge through ionization, protonation, or deprotonation. On the left here, you can see a coenzyme attaching to an apoenzyme in order to create a holoenzyme that is more susceptible to substrate binding. The key difference between an apoenzyme and a holoenzyme is an apoenzyme is the inactive protein without its coenzyme bound, whereas the holoenzyme is the enzyme with its cofactor and is the active form of the enzyme. As you can see, without the coenzyme, the substrate, which is in this funny shape, probably cannot fit into the apoenzyme. A key difference between coenzymes and cofactors is coenzymes are small organic molecules such as NAD+, FAD, and vitamins and other vitamin derivatives. Cofactors, on the other hand, are inorganic metal ions like zinc and iron. Enzyme kinetics. The Michaelis-Menten plot is one of the two important plots that you have to know for enzyme kinetics. And basically, this is just a plot between substrate concentration and reaction velocity. What this plot is saying is as the substrate concentration increases, the enzyme's reaction rate increases, but that is until it reaches a certain point called saturation. At this point, it hits this ceiling. At the point of saturation, it hits Vmax. And that means the enzyme is working at maximum velocity. Addition of more enzyme will not increase the reaction rate at this point. The Michaelis-Menten equation and another derivative below. So this is this top equation is the official Michaelis-Menten equation. And just to describe some of its components, Km refers to the affinity of it's a measure of the affinity of an enzyme for its substrate. A low Km indicates a high affinity of an enzyme for a substrate, whereas a high Km indicates a low affinity. Vmax is, as we talked about before, the maximum enzyme velocity measured in moles per second. This bottom reaction is a derivative of the above reaction, I believe. And here, kcat describes the number of substrate molecules converted to product per enzyme molecule per second, or the rate of In other words, the rate of turnover of substrate molecules to product. And the way to measure catalytic efficiency of an enzyme is to look at the ratio of Kcat over Km. And what this ratio suggests is that a high Kcat means a high catalytic efficiency. A lot of a high turn this means a high turnover of substrate molecules to product. Whereas a low Km, which indicates high affinity to substrate, this causes a higher catalytic efficiency. The lineweaver-burk plot is a derivative of the michaelis-menten plot, and you reach this plot by just taking the double reciprocal of the michaelis-menten plot, the reciprocal of both the x and y axis. This creates a linear graph that tells you a few things. First, it's really helpful for understanding what type of inhibition you're working with if an inhibitor is present, and I'll go into this later on. What it also tells you is that the x-axis is -1 over km and the y-axis is 1 over Bmax. And therefore, this can be used to calculate Vmax and km for whatever reaction you're working with. Cooperative enzymes. Cooperative enzymes are enzymes whose affinity for a substrate either increases or decreases upon initial binding of that substrate to an enzyme. So that's a mouthful, but I can explain. One common example that I can think of is hemoglobin. Hemoglobin is an example of a positively cooperative binding model. What happens in hemoglobin is binding of it has 4 active sites per oxygen, and binding of 1 oxygen molecule to its active site makes all other active sites have a higher affinity for oxygen. This means that the reaction rate increases at a higher rate than it would traditionally. Removal of oxygen from one of the binding sites of hemoglobin will reduce the affinity of all other substrate binding sites to oxygen by that same token. And this is considered a positively cooperative model because you see the spiraling effect. One thing attaches, then another wants to attach even more, and then another wants to attach even more. The way the Kaplan book described it is it used the analogy of a party. As more and more people go to a party, the party seems more appealing. But anyways, that's just one example. There are a few ways to describe cooperativity and to quantify it. And one is Hill's coefficient. If Hill's coefficient is greater than 1, you know that positive cooperation is happening. If the coefficient is less than 1, then you know it's negative cooperation. Whereas if it's equal to 1, then the enzyme does not exhibit cooperative binding. The key difference between the two models can be shown in the graph. Traditional michaelis-menten kinetics will produce a hyperbolic graph, whereas kinetics that involve cooperative enzymes will create more of a sigmoidal graph. Effects of local conditions. In terms of temperature, velocity doubles for every 10 degrees Celsius increase in temperature until an optimal temperature is reached. This is a rule of thumb. The optimum temperature for the human body is 37 degrees Celsius. After reaching this optimum temperature, the enzyme denatures due to high heat and activity greatly decreases. As for pH, every enzyme has a different preferred pH range, and this is because pH affects the ionization of the active site as well as denaturation of the enzyme. Some ideal pHs you should know is most enzymes like to work at 7.4 pH, whereas gastric enzymes that work, in the stomach, like to work at in more acidic conditions, obviously. Pancreatic enzymes have an ideal pH of 8.5. Increased salinity decreases enzyme activity. This is because salt disrupts hydrogen bonding and ionic bonding, causing a partial change in the enzyme's conformation, and in some extreme cases, denaturation. Regulation. Besides feedback inhibition, there are a few other ways to regulate enzyme activity. This involves the use of inhibitors, oftentimes. Competitive inhibition refers to binding to the active site. In competitive inhibition, Km increases. This is because the enzyme has a lower affinity for the substrate. When a competitive inhibitor is present, the enzyme has a much higher affinity for the competitive inhibitor than it does for a substrate. This is why the affinity of an enzyme for a substrate greatly decreases and why Km increases. On the other hand, competitive inhibition does not have any effect on Vmax. This is because if you add enough substrate to a reaction, then if there's enough substrate to trump the concentration of competitive inhibitors, then the reaction can still proceed at its maximum velocity. Non-competitive inhibition refers to binding of an inhibitor to an allosteric site to induce a change in the enzyme's conformation. An allosteric site as opposed to an active site. So in this case, Vmax greatly increases. Hold on, let me make sure I said that correctly. Hey, Vmax will decrease in the presence of an inhibitor. This is because there's less enzyme that's available to react. And the reason why is because as you have more non-competitive inhibitors binding to allosteric sites and essentially disabling normally good enzymes, you have less enzyme available to react. And this causes the maximum velocity to greatly decrease. On the other hand, there is no effect on Km. There's no effect of a non-competitive inhibitor on an enzyme's affinity for a substrate because it does not interact with the active site at all. These enzymes can still attach to their substrates. Mixed inhibition refers to binding to either the enzyme or the enzyme substrate complex with different affinities for each. And its effects on Km depend on the inhibitor's preference for binding either the enzyme or the enzyme substrate complex. If an inhibitor binds the enzyme, then Km increases. Whereas if an inhibitor binds the enzyme substrate complex, then Km decreases. Its effects on Vmax are always the same. Vmax always decreases in the presence of a mixed inhibitor. And uncompetitive inhibition refers to binding to the enzyme substrate complex only and not the enzyme. It always decreases Km and it always decreases Vmax. Irreversible inhibition refers to an enzyme that's permanently altered and one whose active site is rendered unavailable for a long time. Allosteric enzymes are enzymes that have at least one allosteric site in addition to its active site. And these allosteric sites have serve the function of binding either allosteric activators or allosteric inhibitors. And in this diagram, you can see that binding of an allosteric inhibitor to the enzyme's allosteric site induces a conformational change in the enzyme's active site, which then causes the substrate to not be able to bind. On the other hand, if this were an allosteric activator, this would induce a conformational change that would allow the substrate to bind. Covalently modified enzymes are enzymes that have covalent modifications. Some examples of covalent modifications are phosphorylation, dephosphorylation, and glycosylation. A real world, very common example is the G protein coupled receptor. Binding of a ligand to a G protein coupled receptor triggers a signaling cascade that activates protein kinase A. Activation of protein kinase A will then cause a phosphorylation cascade in which many enzymes downstream are phosphorylated and therefore activated. There's no correlation between phosphorylation, dephosphorylation, activation, and inactivation. Sometimes phosphorylation activates enzymes, whereas sometimes it inactivates enzymes. Glycosylation, just to expand on that, is the attachment of sugar moieties. Zymogens are enzymes that contain a catalytic domain, an active domain, and a regulatory domain, which has to be either removed or altered to expose the active site. One example of a zymogen is trypsinogen. Trypsin is a digestive enzyme in the pancreas that, if released uncontrollably, if active forever, would eventually digest the pancreas itself. Therefore, in order to prevent this from happening, it's released as its zymogen form, trypsinogen, and then later cleaved to become trypsin once it's needed. Thanks to SlidesGo for providing me a template for this PowerPoint, and that's it.